So advances in autonomous sensor technology are the driving force behind vehicle manufacturers to reduce traffic accidents and fatalities. In this article, we described the implementation of a collision avoidance system and needed time to collision estimation. Hence, we show one among many other possible solutions to improve detection, and that is to rely on several different sensors, such as a camera and LiDAR sensor. Both camera and LiDAR have its own advantages and disadvantages. The camera has a low price and provides rich semantic information, but it is sensitive to light and has a poor space detection ability. On the other hand, LiDAR has a high cost and is weather sensitive, but it has a high distance resolution and wide field of view. Literature review related to the research subject in this paper represents the cross-cutting between autonomous systems and automotive, and other authors, for example, described a full surround camera and LiDAR-based approach to multi-object tracking for autonomous vehicles. A special part of the research was dedicated to recognizing the importance of choosing appropriate key point detectors. And in this paper, we used Harris corner detector as one of the most popular classic detectors. So this paper describes the implementation of a collision avoidance systems. A collision avoidance system is used to warn drivers in case of collision with another vehicle or any object on the driving path. In order to issue a warning or trigger the brake, the system needs to estimate time to collision. In this solution, constant velocity model is used as an assumption for the physical behavior of the vehicle. Also, the OpenCV library was used, as well as C++ programming language. TTC estimation implementation consists of 3 building blocks: camera, LiDAR, and sensor fusion. Since calculation is based on both the camera and LiDAR sensor, the results are refined using a fusion approach. So for estimating TTC with the camera, the main idea is to compute key points between successive images, and from those key point matches, compute the time to collision by looking into relative distances between key points over time. The goal of key points detection is to detect a unique structure, such as corners, in an image that can be precisely located in both coordinate directions. So as you can see in the figure, the images are loaded into a ring buffer. The buffer gives us images at every point in time, and all these images are routed through an information pipeline into the key points detection phase. Image key point detection is performed by using various methods such as Harris or FAST, and output of all methods is a set of key points which are piped into the exact key point descriptor block. This block takes 2 inputs. The first are key points from the previous block, and the second are images from the ring buffer, so that a key point descriptor can be calculated around each key point location, reflecting different properties around the key point and used for uniquely identifying this key point in the image using its local neighborhood. The output of this block is a set of descriptors, and those descriptors represent input for the last building block, which is called match key point descriptors. This block also takes the set of key points, and based on those 2 inputs, it generates as the output a set of key point matches. This output represents for 2 successive images a number of key points which are found in one image, and then the corresponding partners in the successive image, based on which TTC can be calculated. For LiDAR, we loaded the LiDAR 3D point cloud, and this loading operation gives us a set of 3D points, one for each instance in time. The main goal is to compute distance from preceding vehicle from 3D point cloud at successive moments in time. In order to do so, we need to isolate 3D points in the preceding vehicle, for example, to exclude the road surface. We can do this simply by taking into consideration only points that are above certain height. So these points are surely above road surface. Also, as we look only straight forward, we will discard all points left and right of eagle lane. But the problem with this is that cropping will not be reliable enough, especially when the preceding vehicle is not directly in front of the sensor. So this problem is possible to overcome by using camera-based object classification to cluster LiDAR points and compute a TTC estimate from 3D bounding boxes. We can use a deep learning approach and a neural network, which is able to detect and classify different objects into respective types. These classified objects are provided in terms of 2D bounding boxes in the image. So around each object in the image, we have a bounding box, which denotes the position and the dimensions of the object which we seek. Afterwards, we use these bounding boxes to extract all the LiDAR points which belong to the respective objects. After completing LiDAR point clustering, we have a set of bounding boxes and LiDAR points that are exclusive for every frame, which we use as an input together with image-based key point matches, so we can connect bounding boxes in space, tracked objects, and from those tracked objects, we compute TTC for each object in front of the vehicle. For the purpose of obtaining highly accurate data and taking full advantage of complementary information between 3D LiDAR and cameras, we must use appropriate detector descriptor combinations. And in order to test performances of the implemented solution, measurements were performed on several different test cases. For testing, a forward-looking camera and a high-resolution LiDAR sensor were used. So what is measured is the processing time information and the key performance indicator. Upon inspecting the obtained results, it is observed that the combination of Shitomasi and brief can be preferable almost in all possible situations. This combination of detector and descriptor has the smallest difference in the calculated TTC estimation and the shortest processing time, and consequently the best key performance indicator. Here you can see different detector descriptor combinations and the median difference in TTC estimation. And for conclusion, the fact is that camera and LiDAR are inevitably used in modern autonomous vehicles. We consider the shortcomings of their use and shown that the best way to overcome them is to merge them into so-called sensor fusion approach to improve a collision avoidance system and calculate time to collision as accurate as possible. We also made a comparison of different algorithms for detection and object tracking. In further development, implementation can be improved by using faster detectors, which have been developed in recent years, such as fast, brief, orb, and to enhance the time to collision estimation, more precise and realistic, constant acceleration model can be used as an assumption for the physical behavior of the vehicle instead of current constant velocity model we used now. So that was all, and thank you for your attention.
Thank you very much for your presentation, Ms. Kotur. So you used two different sensors, camera and LiDAR, and we know that the LiDAR has a high price. So did you maybe compare the results when using only the cameras with your solution regarding accuracy of track objects?
No, we didn't. We wanted to put accent on this sensor fusion approach, so we tested only with LiDAR and camera.
Okay, it would be interesting if we can compare it with using the camera only, okay?
Yes, I agree.